That is double trouble right there.
It's him or him. I don't know. We're flipped on here, so we're already confused. How are you guys doing today?
Joe,
And
you have your hands full with this one.
Yeah. Well, hey, listen, I can already hear them, so we're ahead of the game. All good to go. What's up, guys? How you doing?
Doing great.
Well.
Thank you.
Are we live now?
We're live, baby.
Awesome.
Awesome.
This is live. And Francisco, Judy, thank you very much. For the next hour, we'll be joined by the guys from AEM, and to everybody out there on EPARTRADE. I know we're coming to a conclusion here, but we do have Friday left. It is going to be great. Thank you, everyone, for participating. I'm Joe Costello. You'll have the opportunity to ask questions of the guys in the chat section. And if you want to take it in a different direction, if I don't ask the question that you're thinking, by all means, put it in the chat section, and we're going to do it. Okay, so first, because I don't know you guys, so who's Kirk and who's Lawson?
That's Kirk. I'm Lawson. Yes.
Hey, guys. I'm Joe.
Hey, guys.
Nice to meet you. Nice to meet you. Obviously, Francisco and Judy said such great things about you. We've been seeing the commercial, automotive electronics, really high-end stuff. But today we're talking a little bit about more about EV, and I think that's kind of interesting. Why don't you lay it out for us?
Okay. Yeah, we are going to talk about EV, and this is going to be a high-level discussion, very much an overview of the EV system basics for EV conversions and motorsports applications, the major components, how the different systems on the vehicle break down. And it's really intended for shop owners and for people who are interested and really want to know more about EV, but maybe they haven't done the research yet, or they're a little intimidated and they just kind of need that 1,000-foot view. Where do I start looking? What are some of the major components? So without further ado, I'm going to share.
I just want to chime in. There's a slide at the end. There's a couple of components that are really important about this discussion outside of just the EV itself. Our industry is challenged dramatically with the EPA, legislative and regulatory challenges for the tuners, for the engine builders, for race car builders. So we have a situation where you have, you always talk about the carrot and stick. And I've used this analogy a few times with regard to this market segment, or this emerging market segment, is that you have a carrot that there are some really fun, substantial performance benefits from EV propulsion. I mean, it's pretty fascinating, the performance benefits that are there. The stick is the EPA. We haven't got the RPM Act. SEMA has, in their efforts, has not been able to make it happen, and we really do have high hopes that it does come through for us and our industry. That would be great. But without that in place, the fact of the matter is the industry does have some degree of uncertainty with regard to the internal combustion engine use in race cars. That being said, that's the stick. There's another carrot. This is a brand new market segment. There are a very large number of shops and builders that are coming to us, AEM, at EV events saying, hey, I have customers asking to get this done. Where do I start? Where do I go to learn about this? And the fact of the matter is that these hot rod shops, fab shops, race shops, they already do like the hardest part, the fab work, making parts fit and work together. This is sort of the toe in this presentation that we put together, really is sort of the toe in the water to show you the key components required for propulsion and some of the things that we saw coming into this market segment that we believe brings some refinement and some safety to this opportunity, this market opportunity.
No, very exciting. I have seen some try to hold back the tide, if you will. And I think, I love the fact you guys are obviously petrol heads, you love high performance, and for you to entertain and educate on this subject, it's just, I think it's good. I'm very interested. We're all seeing, what's happening from street drags. I host street drags at Homestead Miami Speedway. Kids who roll in with dual motor Teslas and they're blowing the doors off Mustangs and the tire never turns. And there's just so many amazing aspects of it. But there is pushback. Of course, we all know there's going to be pushback, but I love your carrot and stick analogy, because in the end, we like to go fast and accelerate and have fun with our families. It's a family sport after all. So take it away. I'm all ears.
All right, great.
I'm going to share my screen and pull up a presentation here. Let's pull this up. And then I'll put this in. Here we go. Okay, can everyone see that?
I can see it.
Can you see it okay?
Yes.
Okay, so again, this is a high-level discussion about EV conversions and builds, some basic components and things to consider. If you look at the 4 vehicles on the front, we're representing, you know, your EV conversions, street style conversions, as well as motorsports conversions. We've been involved in all 4 of those vehicles. On there, I'm sure a couple of them are familiar to you. The Huff Motorsports dragster on the bottom right was the first EV dragster to eclipse 200 miles an hour, and the Cobra Jet 1400 has so far run a personal best of 812, they give about 179 miles an hour. That Mustang in the top left is a Tesla swapped Mustang that we have in-house. It's one of our development vehicles. We call it the Testang. And it's got a base drive, which is a large drive unit, but the lowest power large drive unit that Tesla makes. That car does 1178, 1180 in the quarter mile, about 117 to 120 miles an hour on very average street tires. So again, going back to the performance of EV, if you haven't been in an EV, the performance is there. I strongly encourage you to take a drive, because I was one of those guys, you know, several years ago. Oh, I'll never have an EV. It'll make sense. And then I took a ride in a Tesla, and that started to change my mind. We started going down this path, and I'm a full convert now. EV is very exciting, and it's coming. So what goes into an EV conversion? Before we get started, I want to talk about, just briefly go over some basic terms and terminology.
Yeah, I'll chime in. So, you know, the petrol head you mentioned earlier, you know, everybody talks about TDC or TPS or WOT, you know, we have all these, you know, acronyms. This form or this market has a bunch as well. Anyone who's watching, I just recommend do a screen cap here. You could see there's a bunch of them. We're going to use them throughout, you know, as we go through here. And one of the kind of key components here is, outside of the acronyms up top, it's also the power terminology. They talk in kilowatts and Newton meters versus horsepower and torque, you know, foot-pounds or pound-foot of torque. We've actually added a little equation on the bottom that lets you, you know, do the quick math in your head, or, you know, someone could just, you know, whip out their phone and do a calculation. What does 100 kilowatts mean? What does that mean? It's 135 horsepower. Things like that'll start to click. And our goal here today really is to show what are the major components to make these things go, stop, charge, and keep them safe. And then some of the features that go along with it. And then also begin to familiarize people with the terminology that's used commonly within the EV conversion market, EV motorsport segment. So that's kind of the gist of it right there.
Absolutely. And I'll also have PDF versions of this, and we provide our contact info at the end. So if anybody needs some information from this, please feel free to grab that, reach out to us, and we're happy to help and answer any questions that you have. So I'm sure you've had time to go through some of these. We'll be mentioning them, and we'll, if anybody has questions, just to ask. We can go back to the slide, or we'll be happy to answer it. And just as a rule of thumb, you know, a watt is equivalent, 1 horsepower is roughly equivalent to 3/4 of a watt, and it's kind of the other way around. 1 Newton meter is equivalent to about 3/4 of a pound-foot of torque. So it's just kind of a general term to start thinking about as you're converting Newton meters to pound feet and kilowatts to horsepowers. So what goes into an EV conversion? Again, this is very general, but some of the things that you need to start thinking about when you think about an EV conversion is, obviously, you're going to need to remove the internal combustion engine and the drivetrain if you were converting the vehicle to a direct drive unit. So a direct drive unit would be like a Tesla. The energy goes directly to the inverter commands the motor to spin, and you have propulsion. I don't want to get deep into our product line, but our VCUs allow you the capability to also control an indirect drive. So that would be a very traditional internal combustion setup where you have an electric motor coupled to a transmission, And then that is sending the power through a traditional drive line to the wheels. That is, as we've discovered, and as you've seen on the Cobra Jet, a big advantage to running in direct drive because, for instance, on that car, we're able to literally idle or preload all 4 of those motors at the line, so it can take a really good hit off of the line, much like a traditional ICE drag car. So you're going to need to consider motor and inverter selection. That's going to dictate how much power you're going to be able to create. Battery selection is critical because you're going to be power limited by your batteries, and you also have to consider fabrication. Where are they going to go? How are they going to be wired? Are you going to have to split the packs? So there's a lot of things. Are they going to be exposed to the elements? And if they are, does that make this a Sunday sunny drive car, or is it completely sealed? Can this thing be driven daily? High voltage component selections. We'll get into what those components are in a second. Again, I would imagine anybody watching this, or most people watching this, the easy part is the custom fabrication. You got to address the 12-volt system, there's safety considerations, and obviously, ultimately, how are you going to control the vehicle? So here's a very basic diagram of the different components that you'll find. We hope you liked our presentation. Thanks for watching. We're kidding. This is a very basic unit. It kind of shows a more standard layout of what you'll see in a car that's been converted. Typically, we'll see battery packs up in the front where the engine used to be. We'll also see them along the tunnel where a driveline used to be in a direct drive application. There's onboard chargers, DC to DC converters. You've got your control units and your electronic components that are going to replace all of your hydraulic, and your driven components in your internal combustion engine. And we'll get to all that right now.
Yeah, you just think of your accessory drive. You don't have to go back. You think about your accessory drive and all those accessories hanging off the front. You're not spinning those with an electric motor. You don't have some big accessory drive sitting out the front for a couple of reasons. One, it's somewhat inefficient. Two, some of these electric motors spin up to 17,000 RPM. So you'd have some challenges with your components staying together at that, or even keeping a belt on it. So that being said, to Lawson's point, there are devices out there, fortunately, available that allow you to replace all those with an electric driven, in some cases low voltage, in some cases high voltage, the 12 volt to the 400 volt range.
So this is a little more detailed diagram of just a high voltage system. So these orange lines represent the high voltage cabling.
Kick in on that. So you'll see a lot of like if you see in this jacket, there's an orange webbing to it, and you see the orange lines for the high voltage. That's actually an industry standard. If you look under the hood of any EV car or any EV conversion or EV race car, you're going to see an orange cabling, up in 2 gauges, a fairly substantial. It's a little bit smaller than a garden hose, but that's where all your current's flowing. So you'll see there's actually an actual picture of a pack. I think that's a battery pack, but you can see all the orange cabling. That indicates high voltage. So that's one trigger right away. So when we do schematics, anything that's high voltage is going to typically be in that orange color.
That's a good way to think about it when you're diagramming or you're outlining the car. Is you want all your start thinking orange when you're thinking your high voltage components. That's an industry standard. Even down to they have an actual process color for the orange for high voltage cabling. Marketing guy, I pay attention to stuff like that. So within the high voltage system, your battery packs are going to provide you with the energy to create the most power potential from the motor to get the best propulsion. Typical EV voltage, high voltage packs are somewhere between 400 up to around 800 volts currently, and they're made up of lithium ion cells that are strung together, and they're strung together in parallel, and then those packs are typically connected in series to one another. Yes?
No, I'm good.
Okay. You'll see, what a couple of the common ones that you'll see coming out of junkyards will be from Tesla, Chevy Volts. There's also offerings from LG Chem, Samsung, Life PO4. There's some other ones out there, but those are some of the major ones. And this is something that Kirk and I talked about, and it's really, really critical, is the C rating of your batteries is very, very important. A C rating, basically, as it states in there, it means that the discharge current will discharge the entire battery in 1 hour if you have a 1C rating. So a 1C rating would be common on like a forklift, something like that, not something you're going to want to put in your EV. A good way to think about this, and this is Kirk's analogy, I think it's perfect, is think about your fuel system for your internal combustion engine vehicle, right? At some point, if you add, you open up the breathing, you add a turbo, you do all this, you've got to add more fuel, right? Your limiting factor becomes your fuel. It becomes like, hey, how big are my lines? What are my AN fittings? Well, how big is my hosing? The batteries are very much like, well, they are actually your fuel system of your vehicle. So the higher the C rating, the higher the voltage, and its ability to transfer and maintain current, that's what's really going to allow you to get to extract the most performance. Now that's more critical in a racing application. And again, we'll get into some of this a little bit further down the road.
Right. Just to expand on that a little bit, when you're talking about the battery, think of it as your fuel tank. You have this massive battery, so you can have massive range. But if you want increased performance as well, which means a higher current dump, that's where we're talking about the C rating. So that's where the analogy is: a bigger fuel pump, bigger fuel lines, big regulator, big injectors, all these things to get the fuel up to the engine. In this case, now you have a battery that has a larger dump capacity to get the energy to the inverter. So that's kind of the back half of your fuel system. So that's just to further expand on it a little bit.
Yeah, and to that end, in our testing, we've seen this on the dyno with different styles of batteries, with energy batteries, something like that comes out of a Tesla, where it's designed for long life. I mean, it gives you that hit, but then it derates itself to sort of protect itself from a temperature standpoint and also a depletion standpoint. Hybrid electric batteries tend to be very, very good for racing applications because they have a higher C rating. They tend to just let it eat. They just feed current longer. And while you're obviously limited from a power standpoint in the motor, what it's ultimately going to make, so it's ultimately an electric motor will make consistent power. Your ability to create area under the curve and carry that power longer. And as we all know, as racers and performance guys, the more area under the curve, especially from that low to mid range, the better acceleration you get, the faster you're going to go, the quicker you're going to get out in front of everyone. That's all evident in the dyno results that we've seen with hybrid electric batteries versus, say, an energy style battery out of a traditional battery electric vehicle. Is that making sense? Okay. So in addition, you're going to have contactors. Contactors are basically just giant relays for the high voltage systems, activation and deactivation. So typically one is going to be required for your batteries in series, also your onboard charger. And these are going to engage and disengage the high voltage system.
Right. So what's really important here is that when the vehicle's at rest and shut down, so in a vehicle, an internal combustion engine, a traditional car, you turn off your key, you take it out. There's shutdowns that occur within the ECU, so the engine doesn't keep running. There's a lot of things that happen. In this case, the contactor's job, based on input from the VCU or some other control device, is to basically insulate the battery from the rest of the drivetrain on the high voltage side. And that's all that's going to do. And then once it's insulated, it's in a position where it can be charged or just set at rest. So that's the contactor's role, is to disconnect the drivetrain, the inverter and the motor from the actual battery pack itself.
So another common component is your onboard charger. These devices basically convert your AC power to DC power.
Yeah, so it's yeah, your onboard charger basically taking your wall, either 110 or 220, converting that over into DC and pumping the DC battery back up, filling it back up, and then there's also usually a lot of the onboard chargers, they call them OBC, also have a DC to DC converter integrated. So it serves two purposes. One is to recharge the battery. Two is the DC to DC step down. So you have this 350 or 400 volt battery, and we referenced the 12 volt circuit earlier. You still have a little 12 volt battery, but there's no alternator anymore. And that little 12 volt battery plays a pretty significant role in waking up the system to turn your controller on, meaning the VCU or whatever your control device is or devices are. And then the DC to DC kicks in, and if you put on your AC blower or you have cooling fans or cooling pumps for conditioning the battery packs or cooling the onboard charger and DC to DC unit itself, all that is powered by the DC to DC converter. So that's actually handling your whole 12 volt circuit. The battery pack, I'm sorry, the 12 volt battery isn't, the DC to DC is. So it's a really critical component.
Very much so. And that we cover that in the next slide. So I'll kind of cruise past that one, and we'll get into the different types of charging systems in a little bit here too. So this technically the charging port isn't part of the high voltage system, but obviously connects to the high voltage system because it provides a means for which to charge the battery. So if you're unfamiliar with the different styles of chargers, level 1 chargers, this is your standard at-home charger, slow, really slow. Standard is J1772, and Tesla also has a proprietary version of it. Level 2s are faster, typically 4 to 16 times faster than a level 1. You can find them also at home. Most common, if you have a 220 outlet in your house or you've wired for a home charger, then those are where you'll find them at the house. Otherwise, you're going to find them out in an office environment. And again, 1772 spec, also Tesla proprietary. And level 3 chargers now are your fast chargers or your Tesla supercharging station, which I'm sure everybody's heard of. These charge at 3 to 20 miles per minute versus like 12 to 80 miles per hour of charging time in a level 2. So they're very fast, and these are only going to be found at like a standard charging location. At least at this time, they'd be cost prohibitive probably to even put in a shop unless you've got a really big shop and you're moving a lot of EV vehicles. So the cool thing is right now, level 3 chargers are being developed as a CCS, which means combined charging system. So what that means is that you will now have essentially 2 ports for a level 1 or level 2 charger. But if you're out and about or you're going on a long road trip, you can plan accordingly to go ahead and hit a level 3 fast charging station and be able to go and maybe use the restroom and grab a sandwich and get back out on the road in time, but still charge it at your house without having to have 2 dedicated ports to charge from. So Kirk mentioned the DC to DC converter. This is really very much like an alternator on an internal combustion engine vehicle. And it's what allows your whole low voltage system battery to remain charged, run your low voltage system. Finally, we get to the motors and the inverters. An inverter is what controls your motor. So it takes the high voltage DC power in, and it outputs an AC voltage to the motor and commands it to spin. And then the motors obviously are what spin and propel the vehicle. There's a couple different types out there, but we'll just kind of leave it at that for now. This is a unit that we're very big on here. A smart shunt is a really good addition and something to consider when you're doing a conversion in a race car build. It can be used as a very simple BMS, but we really like to use it because of its integrated current voltage and temperature sensors. So we use it in conjunction with the BMS as an additional monitoring, and we're able to take that data into a VCU and then command the VCU can perform commands based on that data to protect the battery, to protect your battery system, and essentially protect the vehicle.
Right. So the shunt itself, and the information coming back to, in our case, the VCU, it's really critical because you have, again, like an internal combustion engine where you have a number of different sensors that allow the programming in the ECU to output. If you had a temp sensor that showed a high coolant temp or your intake air temp was climbing, you might pull timing, push fuel, overall reduce power. This is a very, very similar form of information for the VCU. It's looking at currents and it's looking at the current demand. So the torque demand is going to equal a current demand. And if you have a temperature rise or you just don't have the voltage available, the VCU will take this information in saying, hey, I know you're asking for X torque or this much throttle, but I have to derate because the current isn't available or there's a temperature spike. So this really is a component of safety more than anything else, and just information for the VCU and for logging. People out there who are going to do conversions are going to use these things a lot to help them figure out, to Lawson's point, the C rating is adequate for the performance that they're trying to gain, or to make sure that their cooling systems are adequate. So if you have a battery temp pack that's climbing, the shunt is going to be looking at the current. The VCU is going to say, hey, and the BMS, all this information is coming in saying, oh, wait a minute, we have a little bit of a runaway situation over here. So stop asking for all this power, and it can derate based on that, meaning reduce the actual power output by this. And at the same time, it can push a message up to the dash and say, hey, derating due to battery temp increase or X degrees. But the shunt plays a really huge role in providing that bit of information.
Yeah, it's very critical. And to Kirk's point, when you talk about safety and protecting the batteries are going to be the single largest investment for your customer. And getting it right is important, but more importantly, making sure that there's a balance between the performance, but also the longevity of the batteries, and also making sure that they're monitored so that you don't damage them is really going to be critical to ensuring long-term happy customerness. So. Cabling spec, as you see, and Kirk alluded to, we've got high voltage orange here, and it's your very large copper cabling with orange loom. So we've talked about the high voltage system. There's really 3 electrical systems and then components within them. Let's go ahead and get over to the low voltage system, which I would imagine for everybody looking at is pretty common. The great thing about an EV conversion is you can really retain a lot of the low voltage accessories and system and setup in a conversion vehicle. The caveat to that would be the pin scour we're working on. That's what was it
was a 24 volts, so now we have to do a 12 volt conversion on the vehicle itself. So, but that's an exception. It's not the rule.
Yeah, definitely an exception. As we talked about, charging is supplied by the DC to DC, so that's your alternator. And controlling these devices, again, you can wire them up in a very traditional way with redundant sensors if required, if you got to have information going a couple different ways, relays and all kinds of extra wiring. Or the great thing about EVs and EV systems is they've all been developed with extensive use of CAN bus networking. So if you're unfamiliar with CAN bus, it's short for controller area network. It was developed by Bosch, I think in like the early 80s. So it's been around for a while, and it's been used more and more on the internal combustion engine side since the early 2000s, and it's used exclusively in EV applications. And what makes CAN bus great is it allows you to take lots and lots of data from a lot of different points and send them all over the place, essentially over a 2-wire connection. So when you're able to utilize CAN bus, you're able to utilize something like a power distribution unit, like our PDU-8 or a PDM, a power distribution module, you're eliminating all of that additional unnecessary wiring, all of those relays, all of that. And more importantly, as it is specific to our vehicle control unit, it allows our PDU-8 is all programmed through this AEM Cal software in our vehicle control unit. So it really provides a centralized point of control for which to control the vehicle, not just the torque management, all the things that spin the motor and create performance, but stuff like your headlights, your wipers, your taillights, your windows, your air conditioning, all of that stuff can be rewired very elegantly and cleanly through our PDU and then controlled and commanded via our vehicle control unit.
Right. So you think of like if you think of an earlier car, they usually have one fuse panel, one fuse box, and it's up in the wheel well someplace. And then from there, all the wires run throughout the whole vehicle. Our theory was that if someone's doing a conversion or a scratch build, whatever it might be, it would be really great if you can position the power where it's going to need to be distributed. So, think of some of these vehicles, you might need a PDU up in the front for some coolant pumps and fans. You might need one in the rear for, brake lights and contactor box control and some other device. You might want to have one in the center of the vehicle for wiper motor, AC blower, and some other things. So rather than having this single location and then wires running the entire length of the vehicle, you can actually position these modules in these three areas, and then from there, distribute your power. Now, the only thing going to these vehicles from the VCU and from the DC to DC, the DC, there's one cable that it's shown in this image. It's maybe a 12 gauge wire or 10 gauge wire, and then two CAN wires, just two wires that run from the VCU to the PDU to command it to tell it what to do. So it's to Lawson's point, and to some of the conversions that we've done in-house, where we can literally pull out, in one vehicle, I think we pulled out 18 pounds of wire from a race car and added this in, at like 3 or 4 pounds total with all of our cabling and the sub harnesses that went in. So kind of an elegant way to deal with a wiring harness situation.
So back to Kirk's point, we made these small with 8 channels each, but you're able to daisy chain multiples together.
They're about the size of a cell phone, a little bit thicker,
Yeah.
roughly. And this isn't. I don't want to turn the overview into a AEM commercial, but these are, historically AEM's done a good job of listening to their customers and meeting their challenges, and that plays into a big part of our success. So when you're standing in a facility and you're listening to someone complain about wiring the whole car and these massive expensive harnesses, you look at it and say, there's got to be a better way. And you talk to the engineers here, we talk amongst ourselves, and we come up with these solutions. In addition to these, just being CAN controlled, there's something else that's really nice, is that it's a two-way communication. So while the VCU is doing the heavy lifting with the calculating and telling it what to do via CAN, it's also listening to the PDU. So the PDU can give information back saying, everything's cool, everything's great, and there's no problem here, right down to the point where we can actually monitor current and voltage by wire output. So if there's a short circuit, there's a CAN message that comes back to the VCU and say, hey, there's a short or an open for the brake light or for a pump. And again, that information can be pushed up to the dash with a warning signal to the driver of the vehicle or the person doing the work saying, hey, there's a problem, and here's exactly where it is. You don't have to guess. You don't have to go to a fuse and let the fuse blow 3 times. It's going to tell you what's going on, in that circuit, which is another huge advantage of CAN.
Absolutely. So to Kirk's point, as you can see in this diagram, and this mirrors one of our development vehicles, you can see we have PDU strategic. Oops, I'm sorry. Let me get that back. So we have PDU strategically placed in this car up front. So this PDU is controlling the headlights, and it's also, let's see, what do we got on this one? Oh, you got the contactors on this one. Yeah. This one, it would be controlling the CAN keypad. It would also be controlling the dash display, and the PDU in the back would be providing the 12-volt power to wake up the inverter. Looks like the motors and the taillights. Yep. Yeah. So as you can see, the ability to utilize CAN bus and utilize PDMs really simplifies the wiring eliminates weight, which is critical for our race builders, and just provides an overall more elegant and intelligent solution to vehicle development, because it's going to allow you to, if there's a problem, find it really fast and shorten up that downtime, get that car in and out, so that you can be more profitable. So leads us into CAN bus networking. As we talked about, CAN bus lets you send a whole bunch of stuff across a couple of wires, communicate one or two ways. And, even on conversions, and this is one of the opportunities that we saw coming into this, is even in EV conversions, we were seeing CAN bus networking on an EV conversion. Really cool resto car with an EV swap. But it had, the BMS and the batteries were all on one CAN network. And then it had maybe a CAN spoofing device that was integrated into a Tesla style swap. But neither of those systems were speaking to each other. So again, kind of going back to Kirk's point with safety and battery temperatures and available currents, if the inverter doesn't know what's available and it commands it, that's a potential for damage. And that's where things can really, really go wrong. And so, again, the utilization of CAN bus and the ability to pull all of these various CAN networks into one place in the VCU, in our VCU, for instance, it now gives you all the data you need to be able to program conditions to really not only get the best performance out of the car, but ensure the best safety as well. And we'll talk a little bit more about safety in a minute. But, again, going back to this diagram, you can see there's essentially 3 CAN networks in this. There's this green CAN network here. And that's networking various PDUs, the dash, also the pump, the inverters. And then we've got this, or I'm sorry, did I say green and hop to blue? Follow the traces, guys. You can see there's 2 independent networks here. And then there's a 3rd CAN network down here, which is the network connecting the VCU to your laptop to program with AEM-Cal. But again, the beauty of this is you have the ability with CAN bus networking. There's no guesswork. All the data is there. It's really up to you to be able to go into it and sift through it. And once you understand how it's flowing and how to utilize it, not only for programming and setup of the vehicle, but also for diagnostics and troubleshooting, this stuff starts to get a lot easier. Really fast.
Stick on this for a second.
Yeah.
I'm just looking at the time.
Mhm.
So one of the things that we noticed when we started looking at this market segment years ago, is that, to Lawson's point, you had these great devices, but they're working in their own vertical. So you could actually independently program a BMS. You can independently program an inverter. You could independently program a DC to DC. So you could have these devices all working together and not really cross communicating. So there's a term that JR, one of our lead engineers here, coined. He said, there's literally no adult in the room. There's no one saying, hey, you can't do that, you can't do this, and why are you doing this? So that if there's no adult in the room, these things can run on their own and run out of control. So we saw this opportunity, again, if you go back in time in the tuner days where we had the alphabet soup of all different devices on an internal combustion engine for boost control, knock control, sub injectors, you had alphabet soup, they called it. And you had to work really hard to make them all work together to get the performance that you wanted. That's a lot of what we saw on the EV conversion market side as well. So back in the tuner days, in the early days of tuner, we came out with a standalone engine management system that tied everything together, that was plug and play into the factory harnessing. So you could do away with the alphabet soup. You have one location for all your programming and one location for all your logging. This is a reminiscent position that we're taking. We have a single supervisor device that oversees all the devices we're talking about right now that are critical to propulsion and safety. And it's one destination for the data and one destination for the programming. So the adult in the room really is the VCU. So this isn't, forget about it being AEM. If there's a controller out there that can communicate with all these devices and has a user interface that allows you to put in programming to keep them all communicating and then keep them in harmony. And if something goes out of line, keep things safe. That's a device that should be integrated in any EV conversion. So forget about the AEM logos right now. We're just talking about pure safety and simplifying and understanding and knowing exactly what's going on at all times.
Yeah, particularly for a high performance EV build and a motorsports application, it's really, really critical that everything is integrated. So this is your three essentially electrical networks on an EV system together. What we're hoping that you gain from this by us breaking them out and showing you sort of each subsection of the parts is this isn't really as complicated, I think, as a lot of guys think. And really, once you start to wrap your brain around the nomenclature and how it all comes together and what the spec is, these tend to be less complicated than most racing builds and actually just a lot of really, really good custom builds. EV becomes easier.
Yeah, the goal is with devices like the VCU and some of the other devices integrated is to engineer the complexity out. There's thousands of bits of data, running across these CAN networks, so it can be incredibly crowded and incredibly complex to look at, try to sort through all that. But if AEM or other companies, as they go along and they simplify the interface, and those thousands of channels of information that's still going on in the background, but you can just have a knob where you want more or less and keep things safe. That's really ultimately the goal. The goal in the end, we're talking about EV conversion, you talk about naysayers. What we want to do is take the yeah, but out of it. The only thing in the end, if it's done well, the only yeah, but is you lose the exhaust note. Everything else, you're going to wind up with a cleaner, more efficient. I mean, these motors and these devices run well over 90% efficiency. So the cooling systems are minuscule compared to internal combustion engine requirements. And your performance gains can be substantially greater, especially in classic cars. And a classic car conversion done properly, you're not molesting the chassis itself with any kind of fab work. Done proper, it's a snap-in where you're not modifying the body, so you're not upsetting the value of the car long term if you do decide to go back to an ICE and push it across, an auction block or something like that. But that's really the goal. Outside of us just saying, hey, look, here's the major components. It's also, in the end, if we do our job well and the people doing the installation do a job well, the uptake on this, I think, is going to be incredibly fast. Because you do have that stick called the EPA, but at the other end of it, you're going to have really satisfied customers that don't say, yeah, but, there is no cold start, there's no choke cable, there's no oil dripping, there's no fuel cell smells. It just, you get in, you push a button and it just goes. And by the way, it goes really well. So these are all things that play into this conversation, so people understand what the opportunities are.
Absolutely. And to expand a little on what Kirk was saying, the performance is definitely there. I mentioned we did 1178 in our testing Mustang. That car with the 3-valve mod motor was a high 13.8 14-second car. So we're 2 seconds faster than that car in the quarter mile as it came out of the factory. And it's a good car. I mean, I love the S197. It's a great car. It's a blast to drive. A lot more fun with that Tesla swap in there. The other thing I'll allude to is on the conversion side. So you think about engine swaps and things like that, and they're becoming more challenging with the EPA regulations. The Testang is certified as a Tesla for street legal use, is registered in California as a Tesla. That took us a half an hour at the DMV. What?
It's registered as a Tesla? Or an
Yeah,
EV?
is I think a Tesla. I think
Okay.
they're registered as a Tesla, but for sure as an EV. And to provide an anecdote to that, our controller here, Tony, has a track car. He's got a Honda track car. He did a case swap in, but he wanted to get it certified for street legal use, and it took him several months and several $1,000s to do that. We were in and out of the DMV in about 30 minutes with the Testang.
That's
as,
awesome.
as a full conversion legal. That's incredible in California. So a lot of advantages to the street performance crowd. So what are some other things that you may want to consider that you're going to need to consider? Some of the stuff you're going to need: fuses, obviously, and you're going to need to convert, as we mentioned before, some of those hydraulically or belt driven components to electric. The great thing about that is they're already readily available out there. Testing uses a electric power steering pump from a Volvo, I believe.
So, yeah.
It's got an electric cooling fan. It's got a 4 drive-by-wire brake or accelerator pedal. The last thing on this list, and it's super critical, and we recommend it for every EV conversion or any EV build, is an insulation monitoring device, or an IMD. And as it states on there, it monitors the resistance of a high voltage electrical system. But I think Kirk has a real elegant and basic way to say why this is hypercritical.
Yeah. So I just want to touch on the devices that Lawson started with. The fuses, we're talking about high voltage, high current fuses. So in the event of a bad off or a bad accident, and there's a short circuit someplace, these fuses will fail and decouple the battery from the drivetrain. We're talking about, in a lot of cases, direct drive. So you don't have the opportunity to throw it in neutral. There is no, it doesn't work like that. It's coupled up. So if something bad happens, you want to make sure that you can decouple the battery pack from the drivetrain. That's what these fuses are intended to do. The brake pedal and the throttle, we're using late model components from a lot of drive-by-wire cars because they have redundancies built in. We love redundancy, so it's got a 2 0 to 5 outs for throttle inputs to the VCU, so we can actually see if one goes down, we can flag a signal and derate or put it into a creep mode, so you don't have to worry about any kind of runaway or oh no, our time's up. Judy's back.
Hurry up.
Sorry, and then
Chat section is over the top of
That's
it.
so sweet of you.
to what Lawson was talking with the IMD. The IMD is basically looking, it's like a continuity test between the high voltage circuit and the chassis of the vehicle. So if anything is wrong, if there's any energy leaking to the chassis or the body of the car, which can be very dangerous for its occupants, this gives you a flag, and it can again initiate a message to the VCU. The VCU can send a message to the dash, but most importantly, open the contactors to isolate the battery. So it's a really critical safety component.
So that brings us to what we do in the control systems. Until recently, really, until we came around, most conversion control systems were comprised of a couple different things. CAN spoofers, which sort of it's not an uncommon device, a lot like the boxes that we were talking about on internal combustion engines back in the day, where they're basically taking a signal and modifying it and then sending that to the ECU and tricking it into thinking that it's seeing something that's really not happening, so that you can get the vehicle to work. And we all know the inherent drawbacks and potential issues with that. They work, but it's how well do you want the vehicle to work? Yeah.
So having, again, this is not an AEM commercial. This is what's critical, to have a supervisor, an adult in the room that can give, again, trying to take that but out of the equation. Oh yeah, but if you have a car set up with just an inverter as a controller for the motor and a 0 to 5 running from your throttle to the inverter, it'll work, it'll go. But wherever your foot is from 0 to 100% is the torque demand. So with a good controller that has programmable torque demand, you can actually put a torque curve into it. You can have traction control. You can have map switching based on performance curves that you can have in it. You can also have torque by time, torque by distance. There's a lot of features that you can, even creep mode. So as you're going through a parking lot at low speed, it's just your brake pedal. You're not driving with 2 feet trying to get through a parking lot. So there's a lot of features that a good controller can bring in. And like I was saying earlier, it's bringing all the devices together into one location so you can see everything that's going on. But most importantly, it's giving a suite of features that the tuners out there are accustomed to seeing. So when seeing dynamic launch control, which is rolling anti-lag, we have line lock, built into our system as a feature set. So there's all these motorsport features that are in there that the tuners are going to welcome versus just trying to manage the throttle or the torque or the power with your foot. Remember, electric motor, AC motor, these are big, in many cases, big power, and 100% torque on demand sounds like a great idea until you put your foot in it and you're blazing the tires every time versus having something that's saying, hey, I'm going 3 miles an hour. It can only handle 150 foot-pounds of torque. So let's roll the torque in. And we can do that with our control. And like I said, there's others out there, but that's sort of the idea behind it, to give the user a much better experience.
Yes, and that leads us to what our solution. So, and whether it's ours or a comparable solution out there, we really believe that our system and what we've developed has been based on the research of what exists out there, empirical evidence of the vehicles that we've had the good fortune to work on. We've had fantastic partners who brought us up to speed, and we got a really, really intelligent and motivated group of engineers who are full speed on this every single day. And that's what you see on this page. So what you're seeing is essential, the adult in the room, or the adults in the room in the center of that, in our VCU 200 and 300. It allows you to control anything from 1 motor to up to 4 different motors and inverters. But more importantly, it allows you to see everything so that you can truly dial in a vehicle, whether it's a motorsports application or a street performance vehicle, to be something that you can take to the track, but you can drive it to work every day as well. And that's by the utilization of modular battery management systems that are coming soon from us. CAN bus based keypads for propulsion and drive modes, the PDUs that we've discussed for all your switched controls, all of which are programmed in the VCU. So there's no individual programming of each device. You don't have to worry about that. If something goes wrong with one of them, you just pop a spare in and it knows what to do, because all of the programming is done through AMCAL software in the vehicle control units. And then of course we have CAN-based digital dash displays. So that gives you data visualization for any or all, I don't know why you'd want to do that, but any channel you want to see, you can put it up there. More importantly, you can log it. So if you're a builder, if you're a racer, anything that you want to see is downloadable right from the digital display into our AM data analysis software for viewing. And then we have cool stuff like GPS. So if you don't want to mess around with some kind of calculation for speed, you can utilize the GPS module for speed. And again, it's all connected. It all talks to one another. It's all programmed in one central location. And then of course it's bringing in information from all the other networks in the vehicle, so that you have a true 1,000-foot view of everything that's going on. And then you can dial it in and get that car really performing much better, I think, than you're going to get with any other type of solution in the EV space. And more importantly, you're going to have fun with it. It's going to be fun to drive. So let's get to the end here. So that leads us to this, and why are we doing this?
We started with this. I mean, I jumped way ahead, just thinking, look, you're going to be watching about these EVs. We're going to share what the primary major components are. But really, the fact of the matter is, you can't stop this. It's happening. We are AEM. You want to be at the leading edge. We're at the bleeding edge right now with the level of investment that we made here because we believe in this segment. We're all switched on. You mentioned we're petrol heads. You're petrol heads. Everyone here races something with an internal combustion engine, and at the same time, we are absolutely blown away with what we're able to accomplish on the EV side. So it's happening. And then if you really want to show off and not worry about looking over your shoulder and the EPA knocking on your door and handing you a demand letter because the RPM Act's not in place, this is where you go. And it's really fun. And your customers aren't going to have to worry about where are they going to get their car inspected or what do they have to worry about to get moved forward. This is all hands above the table and a really fun new market segment.
Excellent. Gentlemen, wow.
Thank you, thank you. I
Exactly
hate-
what I was hoping it would be.
I hate to be the bad guy here, but it's 5 o'clock and we just have to wrap everything and then move into our next session. So you want to add a few more words, Kirk or Lawson, to close this?
The only thing I would say is we've tried historically when there's a new market or a new product on the market segment, we try to give as much information about the features and benefits of the product. Like I said, it doesn't have to revolve around AEM. That being said, if you go to our website, AEM EV, there's a section understanding EVs, and there's a really nice knowledge base there that's been put together by our engineers, and Lawson has wordsmithed it so it's easier to digest. So there's a lot of information there. I would encourage you to go check it out. And if you're not watching our AEM Power TV video channel, we're doing all sorts of different builds there as well. I would encourage you to check that out too. We have fun doing it, but we're displaying what we're capable of.
The concept for EPARTRADE is basically, in my opinion, there's a big hole in the internet. So the internet started many years ago, but there's never been an online business community for racers on the World Wide Web. The need for EPARTRADE is actually quite obvious. Basically, people in the business of auto racing need a place online to hang out and get their problems solved.
It's extremely simple for a buyer or for a supplier to interact on the platform. The first thing you need to do is sign in, which is free. And the second thing is, when you see a product that you're interested in, all you need to do is click on request more information. If it's a company, you click on request more information, and then from there, it is forwarded directly to the buyer or to the supplier.
You can go to epartrade.com, you become part of a community of businesses in racing, and it makes sourcing products much easier than just on the internet or using Google.
At EPARTRADE, there is no e-commerce. It's literally a connection just like at a trade show. So now, any time of the year, a buyer could reach out to a supplier through an email.
More than that, it's a place to go just to keep current every day. So it's a good place to start your workday in your racing business or in your offices of your professional race team. And you know you're current when it comes to new technology, industry news, technical papers, technical videos, all of that and more. We're not looking for a million hits per day. All we want is people who are really the volume buyers of racing products in the racing industry to be part of the little world of EPARTRADE. We have racing businesses participating from around the world. So you get suppliers from around the world, you get buyers from around the world.
EPARTRADE really eliminates having to travel, closing down your shop. Now you have a place to showcase globally your racing product and technology.
There are two types of people, racers and everyone else. Racer Magazine is for those who believe that racing is a way of life. Racer embodies the excellence that defines a sport driven by passion, courage, and ingenuity. Get 1 year of both Racer's print and digital edition for only $39 with instant access to our entire digital issue archive. Subscribe now at info.racer.com.